All right, let's unpack this. When we look up at the night sky, it's easy to forget we're looking back in time, really.
Hmm.
But how do scientists actually figure out the age of things way out there?
Yeah, it's a great question.
I mean, for our little corner of the cosmos, our solar system, we've got decent methods.
We do.
Geological records on Earth, radioactive dating, even those ancient meteorites give us a timeline, pegging the oldest stuff around, what, 4.56 billion years?
Pretty much, yeah.
Yeah.
About 4.5 billion. But when you zoom out to the scale of the entire Milky Way galaxy,
Hmm.
well, the challenge gets astronomically bigger.
Right.
What's fascinating, though, is the ingenuity scientists have shown. They've developed ways to measure these immense stretches of time.
Like what? What are we talking about?
We're talking about looking at the faint glow of the oldest white dwarf stars as they cool down over, like, trillions of years.
Wow.
The oldest ones we see have been cooling for about 12.7 billion years.
Okay.
Then you have these ancient crowds of stars,
Yeah.
the globular clusters. They're estimated to have formed around 13.4 billion years ago.
Even older.
Yep. And if we consider the expansion of the universe itself,
Mhm.
something we can measure using these pulsating stars, Cepheid variables,
Hmm.
that gives us an age of about 13.7 billion
It's
years.
getting very close now.
And finally, there's the afterglow of the Big Bang itself, the cosmic microwave background radiation. That pins the universe's age at roughly 13.77 billion years. It really recalibrates your sense of time, doesn't it?
Absolutely. So we have these different cosmic clocks, all pointing to a very, very old universe.
Yeah.
And this all fits into our current understanding, right? The standard model of cosmology.
Exactly. The standard model, often called lambda cold dark matter, or TDM.
Right. Lambda CDM. It's like the universe's recipe, isn't it? With ingredients like dark energy, cold dark matter, and the ordinary matter we actually see and interact with.
That's a good way to put it. And it's been incredibly successful at explaining how the large-scale structures we observe today, like galaxies, actually came to be.
So these big cosmic models, they provide the framework for understanding how galaxies like our own Milky Way even formed and assembled over time.
Precisely. And when we look at the different parts of our own galaxy,
Yeah.
the thin disk where we live,
Uh,
the thicker, older disk,
Yeah.
that central bulge and bar, and then this enormous spherical halo surrounding everything,
uh-huh.
which is sprinkled with remnants of smaller galaxies we've captured, these stellar streams. All of these pieces hint at a really complex history playing out within that broader cosmic timeline.
Which brings us neatly to the mission of this deep dive, then, to really get into the story of how our own Milky Way formed.
Yeah, let's do it.
We want to understand the sequence of events, and crucially, the ages and origins of its main components. The thin disk, the thick disk, that big stellar halo, and those stellar streams.
Okay.
So where do you even start? How do you figure out how old an individual star is? It's not like they have rings like trees, counting the years.
Huh. No, they definitely don't.
Yeah.
That raises a fundamental question. And the answer involves some incredibly clever detective work using what we call stellar evolution models.
Okay, models.
The basic idea is that a star's life story, from birth to death, is mainly determined by just two things: how much mass it starts with and what it's made of, its chemical composition.
Mass and chemistry. Got it.
So, by carefully observing a star's current properties, like how bright it actually is,
Right.
its intrinsic luminosity and its temperature, which we get from its color,
Mm-hmm.
and then comparing those observations to these really detailed mathematical models that predict how stars of different masses and compositions change over billions of years, we can technically run the clock backward and estimate its age.
Okay, so it's like having a library of cosmic biographies. You see where a star is now, compare it to the models, and figure out how far along it is in its life story.
That's a great analogy, yeah.
And I remember hearing about the Hertzsprung-Russell diagram, or is it the color magnitude diagram? How does that fit in?
They're very closely related concepts, often used interchangeably in practice. Think of it as a graph where we plot a star's true brightness, its absolute magnitude against its temperature or color.
Okay.
As a star ages and evolves, it follows specific paths or tracks on this diagram. So
Yeah.
by plotting a star's observed brightness and color and seeing where it falls relative to these theoretical evolutionary tracks.
You can pin down its current stage of life and therefore get a pretty good estimate of its age.
Exactly.
That makes sense, comparing real stars to these theoretical life paths. But how do we get accurate measurements of those real stars, especially how far away they are? I know distance is crucial for figuring out their true brightness, not just how bright they look from Earth.
Ah, yes. Distance is key. And this is where space missions like Gaia have been absolutely groundbreaking, a total game changer.
Gaia, I've heard so much about it.
It's revolutionized astronomy. Gaia has given us incredibly precise measurements of stellar distances using a technique called parallax for, well, hundreds of millions of stars across huge swaths of our galaxy.
Hundreds of millions. Wow.
Yeah. Knowing the distance precisely is the key to unlocking a star's true brightness, its absolute magnitude. And with this wealth of accurate data, we can now piece together the ages of individual stars and entire groups of stars, not just based on where they are, but also how they're moving their kinematics.
Right, location and motion. Which brings us to this fascinating 2019 research by Gallert and colleagues. They used Gaia's second data release, DR2, right?
That's the one.
And they focused on large groups of stars in the halo and the thick disk, but within a relatively close distance to us, about 2,000 parsecs, which is, what, 6,000 or 7,000 light years?
Roughly, yes. A parsec is about 3.26 light years. Focusing on this relatively nearby volume allowed for those really accurate distance measurements you mentioned, which means accurate absolute magnitudes.
Okay, crucial for the age dating. So how did they actually pick out the halo stars from all the others in that volume?
They used motion. Halo stars tend to move differently from disk stars. They have these very high tangential velocities, meaning they're zipping around the galactic center, but often on much more elongated, tilted orbits compared to the flatter, more circular orbits of disk stars.
So they're not moving with the flow, so to speak?
Pretty much. Gallert and her team selected stars with these sideways speeds greater than 200 kilometers per second relative to the sun. That's fast.
Very fast.
This gave them the sample of about 60,000 stars that were very likely members of the stellar halo.
Okay, the high-velocity stars. And for the thick disk sample, how did they define that?
They used the same distance limit within 2,000 parsecs, but they looked at stars that were significantly far away from the main plane of the galaxy, more than 1,100 parsecs either above or below it.
So way out of the flat plane where most stars are.
Exactly. And they specifically excluded stars that were already in their halo sample based on velocity. The idea is that at those heights above the plane, the thick disk population is dominant, not the thin disk. This gave them a much larger sample, about 500,000 stars.
And you mentioned something interesting earlier, that this thick disk sample was defined purely by its location, its morphology, not by chemistry or kinematics. Why is that important?
It's significant because traditionally, astronomers often used a mix of location, motion, and chemical makeup to separate these components. By defining the thick disk sample purely based on where the stars are, Gallert's team could make a more direct comparison between this structurally defined group and the kinematically defined halo sample without prejudging based on chemistry.
Okay, interesting approach. So they've got their samples, halo stars picked by speed, thick disk stars picked by location. They plot them on the Gaia color magnitude diagram. What did Gaia reveal about the halo population specifically? Anything surprising?
Oh, absolutely. What Gaia showed very clearly is that the halo isn't just one big jumbled mix of old stars.
Mm-hmm.
Instead, it appears to be made up of at least two distinct subgroups. These showed up as two separate sequences, or bands, of stars on the color magnitude diagram. A blue sequence and a red sequence.
Blue and red. Okay. Two distinct groups.
Exactly. This immediately suggested the halo had a more complex origin story than just, say, a single collapse event.
And blue and red?
Yeah.
That relates to temperature, usually. Hotter stars are bluer, cooler stars are redder. Does that directly tell us about their ages here?
It's related, yes. Generally, hotter, bluer main sequence stars are more massive and burn out faster, so they tend to be younger. But when you're looking at these incredibly ancient populations, like in the halo, the stars we're seeing are mostly lower mass stars that live a long time.
Yeah.
In this context, the color difference is also significantly influenced by their chemical composition specifically, their metallicity, the amount of elements heavier than hydrogen and helium they contain.
Ah, okay. So it's temperature and chemistry affecting the color here.
Right. But the key point is that having two distinct sequences, blue and red, strongly hinted that there were different underlying populations within the halo, possibly with different formation histories or origins.
Okay, this sounds like it connects to that whole long-running debate about how galaxies like ours actually form.
Okay.
Was it like one single rapid collapse of a giant gas cloud way back when the monolithic collapse idea?
Mm.
Or did galaxies grow more gradually over time by merging with and sort of swallowing up smaller galaxies?
That's the satellite accretion or hierarchical model, right?
Exactly, that debate. And over the last couple of decades, the evidence has been piling up, pointing more and more towards that second scenario, satellite accretion, galaxies built through mergers.
We found evidence before Gaia, haven't we?
Oh, yes. Even before Gaia, discoveries from the earlier Hipparcos mission back in the late 90s hinted at leftover debris from ancient mergers.
Yeah.
And studies looking closely at the chemical fingerprints of those high-speed halo stars also suggested there wasn't just one uniform population out there.
Okay. And the blue sequence that Gaia revealed in the halo that's been linked pretty strongly to one specific major event, hasn't it? The Gaia-Enceladus merger. Yes, that's right. The blue sequence stars are widely believed to be the remnants of a dwarf galaxy, nicknamed Gaia-Enceladus, or sometimes the Gaia sausage that collided with the early Milky Way.
Gaia sausage. Interesting name.
It relates to the shape of the star's orbits in velocity space, apparently.
Yeah.
But yes, this Gaia-Enceladus merger is now seen as a really significant event in our galaxy's early history, probably happening around 10 billion years ago.
Okay, so the blue sequence seems to be debris from this incoming smaller galaxy. But what about the red sequence? The research you mentioned said its origin was less clear initially.
That's right. There was some uncertainty. One leading hypothesis was that maybe the red sequence stars were originally part of the early Milky Way's own disk, or perhaps its central bulge.
Mm-hmm.
The idea was that the massive merger event with a Gaia-Enceladus could have acted like a kind of cosmic blender, violently disrupting the existing Milky Way disk.
Right.
It could have gravitationally heated some of those original disk stars, kicking them up to much higher speeds and onto more inclined eccentric orbits, so they'd look like halo stars based on their motion, even though they started in the disk.
So original Milky Way stars, but scrambled by the merger.
That was the thinking.
Yeah.
They might be ancient disk or bulge stars that got dynamically heated and tossed out into the halo.
Okay, so here's where it gets really interesting. What did Galler and her team's 2019 analysis actually reveal when they compared these red and blue halo sequences using those detailed stellar evolution models?
This is the absolute key finding. It was really remarkable. They compared the positions of the stars in both the red and blue sequences on the color magnitude diagram against these state-of-the-art stellar evolution models. And they discovered that while the blue and red sequences clearly have different chemical compositions, the red sequence stars are significantly richer in metals than the blue sequence stars.
Okay, different chemistry.
They're actually the same age.
Wait, really? Same age, but different chemical makeup. That's unexpected.
It really is counterintuitive at first glance.
How old are we talking? How ancient are these populations?
Extremely ancient. Their models estimate that both these halo populations formed incredibly early in the universe's history. The peak age they found is around 13.4 billion years ago.
Wow, that's right back near the beginning.
It is. Half of the stars in both sequences were already formed by about 12.3 billion years ago. And significantly, they also found that star formation seemed to stop in both populations around the same time.
So they formed together very early and stopped forming together despite having different amounts of heavy elements.
Exactly. The fact that they are coeval, the same age but chemically distinct, is a hugely significant insight. It tells us age isn't the only factor. Their different chemistries point to different origins, even though they were born around the same cosmic time.
It's like finding two groups of people born in the same year, but one group grew up in a bustling city and the other on a remote farm. They'd have different experiences and resources, right?
That's not a bad analogy. The resources here being the heavy elements available in the gas clouds they formed from.
So how do we make sense of that? Different chemistries, same age. You mentioned the red sequence stars are more metal-rich. How does that connect to their origin? There's a link between a galaxy's size and the metallicity of its stars, isn't there?
Yes, there's a well-established relationship.
Yeah.
Generally speaking, more massive galaxies have stronger gravity.
Okay.
That means they're better at holding on to the heavier elements produced by earlier generations of stars and supernovae, incorporating them into later generations. Less massive galaxies tend to lose more of those heavy elements through galactic winds.
So more massive galaxy equals more metal-rich stars, generally.
Pretty much. So the fact that the red sequence halo stars are more metal-rich than the blue sequence stars strongly implies they formed inside a more massive progenitor galaxy.
Ah, which leads directly to the big conclusion from Gallard et al., right? Both of these populations were involved in that Gaia-Enceladus merger event. But the red sequence stars belong to the main progenitor of the Milky Way, the bigger galaxy in the collision.
Yes.
And the blue sequence stars belong to the smaller galaxy that was accreted Gaia-Enceladus itself.
Precisely. The red sequence represents the indigenous population of the early proto-Milky Way, while the blue sequence is the accreted component.
And the difference in their metallicity even gives us a clue about the size difference between the two colliding galaxies.
It does. Based on that metallicity difference, the estimated mass ratio between the Proto-Milky Way and Gaia-Enceladus was about 4 to 1. Our galaxy's ancestor was significantly more massive.
Okay, that paints a much clearer picture. And this ancient collision, this merger, that's likely what caused some of those original proto-Milky Way disk stars, the red sequence ones, to get heated and end up looking like halo stars today.
That's the strong inference, yes. The huge gravitational disturbance during the merger would have pumped energy into the orbits of some stars that were already present in the main progenitor's early disk.
Scattering them onto those high-speed, tilted, halo-like orbits we see now.
Exactly. It scattered them dynamically, puffing up the early disk and contributing those stars to what we now classify as the interstellar halo. It's fascinating, actually, because even before this Gaia DR2 analysis, some cosmological simulations, based on earlier Gaia data, had already predicted that a significant fraction of halo stars should have originated from a disrupted early disk.
So theory and observation came together nicely there.
They really did. It shows how observations and simulations work hand in hand to build our understanding.
So, okay, let's try and put this revised timeline together based on this research. We have a primitive proto-Milky Way forming stars for maybe its first 3 billion years or so.
Roughly, yes. A period of initial star formation.
Then, around 10 billion years ago, it has this major encounter, merges with a smaller, less chemically enriched galaxy Gaia-Enceladus, which had also been forming stars for a similar period.
Correct. Two galaxies, both actively forming stars early on, colliding.
And the consequences of this merger were profound. It didn't just add the Gaia-Enceladus stars, the blue sequence, to the halo.
No, it also gravitationally heated some of the existing proto-Milky Way stars, likely from its early disk, adding them to the halo as well, the red sequence.
Right, the indigenous heated component.
And importantly, the merger didn't completely destroy the disk structure. It seems the gas involved, perhaps gas brought in by Gaia-Enceladus or gas already present, allowed the Milky Way to maintain or quickly reform a disk configuration. And this disk continued forming stars, becoming what we now call the thick disk.
So the merger triggered or significantly boosted the formation of the thick disk.
It seems to have played a crucial role, yes. The merger stirs things up, adds gas, and likely fueled a significant period of star formation in this puffier, hotter disk structure, the thick disk.
And we even have a rough timeline for the later disk formation from this work, right? The thick disk seems to have reached its peak star formation rate after the merger, maybe around 9 billion years ago.
That's the estimate, yes. About 4.5 billion years after the very first stars began forming in the proto-Milky Way and its neighbors.
And then later still, maybe around 8 to 6 billion years ago, things calmed down further. The gas settled into an even flatter configuration.
Exactly. The remaining gas, or perhaps later gas accretion, settled down into the much flatter, dynamically colder structure we know as the thin disk.
Which is where the sun formed, and which is still actively forming stars today.
Correct. The thin disk represents the most recent major phase of star formation in the Milky Way's main body.
Okay, wow. That sequence really reframes how we think about the galaxy's assembly. It wasn't just one smooth process.
Not at all. It was shaped by these major violent events early on.
So just to recap the really big takeaways here, the Milky Way's halo isn't monolithic. It's got at least two ancient components. They formed at roughly the same very early time, but they have different origins and different chemistries, one from our galaxy's main ancestor, the other from the Gaia-Enceladus merger.
Key point number one.
And second, that massive merger event wasn't just about adding stars from another galaxy. It fundamentally reshaped the early Milky Way, heating its own stars to contribute to the halo and playing a critical role in triggering or shaping the formation of the thick disk.
Absolutely spot on. That merger was pivotal in setting the stage for the galaxy we see today.
The progress we've made in figuring this out, this whole field of galactic archaeology, it's pretty stunning. And largely thanks to Gaia, it sounds like.
It really is remarkable. Gaia's data has provided the precision needed to disentangle these ancient populations based on their motions, positions, and properties derived from those. It truly highlights the power of combining these incredibly precise, large-scale observations with sophisticated theoretical models of stellar and galactic evolution.
We're really piecing together the long, complex, and sometimes violent story of our own galactic home.
We are, step by step.
It really makes you wonder, though, considering the Milky Way clearly has this history of cosmic collisions and mergers, what might the future hold?
The future.
Especially with our giant neighbor, the Andromeda Galaxy, apparently hurtling towards us for a future collision.
Indeed. That's the next predicted major merger on the cosmic horizon for us, although it's still billions of years away.
Billions, thankfully. But it's definitely something to ponder, isn't it? What will our galaxy look like billions of years from now after that next big cosmic encounter reshapes everything all over again?
A fascinating question. Perhaps the ultimate exercise in galactic archaeology predicting the future based on the past.